Hello, everybody. So, in the next couple of weeks, we're going to deal with trace elements and isotopes. Because this is something that you'll see a lot in your professional career in one form or another. We'll start with igneous rocks because we did some igneous rock modeling a little bit earlier. And I want to show you a couple of, well, one single resource. There is a spreadsheet here. It will be trace elements for 250T. And there are partition coefficients that I picked up from this site here, Geochemical Earth Reference Model, or GERM. If you just type this into Google, Geochemical Earth Reference Model, you'll see a couple of hits on Google, and one is to the paper, but the one at earthref.org, that's the one that'll lead you to this database. And if you click on partition coefficients, at some point, once this loads up, you will see a periodic chart. And if you click on an element like, let's say, chromium, then what will open up is a spreadsheet that shows experiments, dozens or even hundreds of experiments that show the mineral melt partition coefficient for different kinds of minerals. So here are the minerals here. Here's the kind of liquid or rock type that was used in the experiment. And so in this case, let's say amphibole equilibrates with alkali basalt. The partition coefficient for chromium was 0.1. So that means that the liquid, in this case an alkali basaltic liquid, had 10 times the amount of chromium than did amphibole. So this is the ratio, this value here is the ratio of the concentration of the mineral divided by the concentration of the liquid. For biotite, however, just to take a counterexample, it had a value of 5.4. So the ratio, concentration of chromium in biotite divided by an alkali basaltic liquid, that ratio comes out to 5.4, meaning the biotite has 5.4 times the concentration of chromium for in comparison to the liquid. So chromium likes to go into biotite. We'd say that it's compatible. Anytime this value is over 1, that's a compatible element. And then amphibole does not like chromium. So we say that chromium is incompatible in amphibole. And we call anything incompatible when this value here is less than 1, and that's much less than 1. All right, so the way we're going to use that, I'm going to just close that out entirely, is that we're going to use it to model trace elements in this spreadsheet here. And so what I've done for the minerals olivine, OPX, clinopyroxene, garnet, plage, and amphibole is I've gone through that database and I've put in trace elements for, I've put in the partition coefficients for all of these trace elements. Rubidium, thorium, uranium, barium, etc. Now, I didn't choose these arbitrarily. These are the trace elements that we're going to model that are from the Tuolumne intrusive complex. So let me finish this brief video by just orienting you to this spreadsheet, trace elements for 250T. We have a range of elements, and the ones I've chosen are ones that are reported that are in this spreadsheet here. Bateman, 1988. TIC is for the Tuolumne intrusive complex. These are from papers published by Bateman and co-authors in 1988. These are the GRF samples, and they report the major oxides. I don't know if we'll get to those. I think we've done major oxide in the past, so I want to do trace element and isotopes before the semester ends. And so these are the trace elements that they analyzed. I'm going to treat potassium and titanium oxides and manganese oxide here as a trace element, even though they're in weight percent proportions. So it's the reason I've chosen these are because these are the ones that we have for the system that we'll analyze for this first exercise. So that's just a label. We're going to divide the concentrations of the elements of interest by what we see in mid-ocean ridge basalt. So that's Morb. This is from a paper by Gale and al. In 2013. So this is just, all of these are in ppm except for potassium and phosphorus and titanium and manganese. Those are all in weight percent. Everything else is in ppm. And so MORB, the average MORB, if you go around the globe and collect thousands and thousands of salts, they have an average concentration of 2.88 ppm rubidium. And they have an average concentration of 0.16 weight percent potassium. They have an average of 129 ppm strontium, etc. So those are the concentrations in MORB. There's another paper published in the following year by Rudnick and Gao, 2014, and they give concentrations of the upper crust. And you can see the upper crust has a much higher concentration, 84 ppm of rubidium, compared to the 2.88 found in MORB. That's average upper crust. Upper crust is going to vary, MORB are going to vary, but if you put all of the upper crust in the entire world into a blender, then you'd probably get something close to that. This part here, now these are just reference values for us. This part here in green is a sample, and it's a sample I've taken from the Tuolumne intrusive complex. I picked something that is fairly evolved, something with about 76 weight percent silica, and it has a higher, an even higher concentration of rubidium, 150 ppm. And what we're going to do in these rows here, let's see, what have we done here? Here I've compared, there's the ratio of upper crust divided by MORB, and then down here I've taken the sample and divided it by MORBs. This is our sample divided by MORB. This is called normalization. So I think what we'll do is I'll end here with just some final comments, and then I'll start a new video on calculations and graphing. If you take a look at trace elements, there's this odd jigsaw effect. And so when you look at elements that have an even number of protons and neutrons, the solar system has an abundance of those, and it's depleted in things that have an odd number of protons and neutrons. It's called the Otto-Harkins rule. So it gives us this kind of seesaw shape, and we want to see past that. So we're not, when we look at rocks, we're trying to smooth out the trace element patterns. And so we do that by normalization. Now, you might be most familiar with something called chondrite normalization. We're not going to do that here. Chondrite normalization is good, but I think it's sometimes a little more useful to use normalization divided by MORB. So if we just take a look at, let's say, our sample from the Tuolumne intrusive complex. It's got 150 ppm rubidium and then 19 ppm thorium, 2.6 uranium. Look at barium. It bounces back up to 325, back down to 3.8. These numbers bounce around. They bounce around for two reasons. One of them has to do with the fact of whether or not they have an even or odd abundance number of protons or neutrons. We don't care about that part. The other reason these things move up or down is depending on how they were created, either by partial melting of the mantle or by fractional crystallization. Now, since our samples here are from the Tuolumne intrusive complex in the Yosemite National Park area, these are granites. They're probably formed by some kind of crust melting or fractional crystallization. And that's the part we really care about. So to model these elements in green, when we come back in the next video, we're going to look at doing some calculations and then how to make some charts. So that would be a part one and a part two at least, maybe even a part three.